It's my pleasure today to introduce today's plenary speaker, Kat Vreugdenhil. So Kat completed her PhD at ANU in 2017. She was awarded the Amos Uwe Radic Award for the best PhD thesis. She then went overseas for a 3-year postdoctoral research position at the University of Cambridge, working on the melting of Antarctic ice shelves. In 2020, she joined the University of Melbourne as a Doreen Thomas Research Fellow. And then a couple of years later, she was awarded an ARC DECRA Fellowship, and she's now an ARC DECRA Fellow in the Department of Mechanical Engineering. Her research interests are in geophysical fluid dynamics and oceanography, in particular the use of innovative turbulence-resolving simulations to better understand ocean physics. Her DECRA Fellowship is titled Resolving Ocean Convection, New Knowledge for a Changing Antarctica. She's also involved in lots of other research initiatives, including the Australian Centre for Excellence in Antarctic Science, and as a chief investigator on the ARC Discovery Project, the basal melting of Antarctic ice shelves. And today she's going to talk to us about ocean convection, circulation and ice shelves, a fine-scale numerical simulation approach to modelling ocean processes. Thanks, Kat.
Fantastic. Thank you, Ryan, for the kind introduction, and thanks everyone for coming out for the first session after the workshop dinner last night. Very much appreciate you all making the effort. It's my pleasure to give this talk today. It's going to be a little bit of a broad overview of research that I've been doing and my group has been doing for the past few years. So it's kind of a whistle-stop tour of a bunch of different work that we've been doing using these fine-scale numerical simulation approaches. And I will mention, as Ryan said, so I'm here at the University of Melbourne. I sit over in the mechanical engineering department. And I'm part of like a big fluids group there that does a lot of fundamental turbulence problems. So at first it might seem a little strange that I sit over in Mech-Eng, but I actually use mainly computational fluid dynamics solvers to do my work. So even though my work is in the ocean application, I always argue that it makes sense for me to sit in the fluids group in Mech-Eng. So just to give you a bit of context. And so the fine-scale numerical simulation approach that I'm talking about today is going to be based on these computational fluid dynamic solvers that are often used for a lot of different engineering problems. All right, so I have a long list of different co-authors that I'd like to thank. They've helped out on various bits and pieces of the work that you'll see today. Great, all right, so I've decided to structure this talk into 2 parts. And so the first part is going to be on ice shelf melting into an ocean. The second part is going to be more broadly on large-scale ocean convection and circulation. And I'm going to be using, kind of just giving, again, a broad overview of the work that we've done in these regions. So these are kind of my 2 main research topics, ice shelf melting and ocean circulation. I'm going to be using part 1 as kind of a springboard into describe different types of fine-scale numerical modelling approaches that we can have. And then the second one, I'll very briefly talk about dynamical similarity and what we can use there. Great, okay, so let's go straight into part 1 on ice shelf melting. So before I get into the fine-scale modelling approach, I did just want to kind of outline some of the challenges that we currently have in understanding ice shelf melting processes. So we have a nice schematic here showing an ice shelf protruding out over our ocean. And so what you can see here is we have a lot of different kind of ocean processes that can affect the basal melting of these ice shelves. So the ocean is relatively warm. I say relatively warm, it's still, you know, can go into negative degrees around Antarctica, but compared to the ice shelf, it's relatively warm, and of course it's salty, and so it can melt the base of the ice. But it's really difficult to try and quantify the melt rate of these ice shelves and how they're going to change in the future because of several different challenges. So the first one is that because these ice shelf cavities beneath our ice shelves, it's kind of the ocean cavities down there, they're so difficult for us to access. It's really hard to make actual in-place observations down there. A lot has been done in the last 5 years in progressing observations in terms of like autonomous underwater vehicles, and that's fantastic, but it's still not enough to completely close and constrain the problem. The second big problem is that as you can kind of see from this schematic, there's a lot of different kind of ocean scale physics going on. You've got very small scales of mixing, you've got things like tides moving around, you've got large scale meltwater plume, and then like a large scale cavity size current. And so all of these different kind of physical mechanisms can interact with each other, and a lot of them, in fact, pretty much all of them that we've looked at, can influence the melt rate of the ice shelves. I should also say that I'm kind of taking an ocean perspective on ice shelf melting, and so of course most of the dynamics I'm talking about are kind of ocean length and time scales, but of course we have some great ice sheet modelers here as well who do more from the ice sheet type perspective, which is also very important to our climate system. So these two main challenges really feed into the fact that it's really difficult to have parameterizations of ice shelf melting in large-scale ocean models, and there's been a couple of really nice review papers recently looking into these points. So our approach is to run fine-scale ocean models to really try and improve our understanding of these challenges. So I'm just going to give you, again, a whistle-stop tour of kind of different fine-scale models that we could use here. So first I thought it would help to talk about what I actually mean by fine-scale models. So you can think of it as kind of, I don't know, like an ultra high resolution model. Basically, we have, I didn't want to not include lab experiments here, even though I don't really do that much lab work anymore, but I really wanted to stress that this is one type of fine-scale model that you can do. You can also do direct numerical simulations, but if you're doing these kind of lab scale models or direct numerical simulations, which is resolving all of the turbulence in your system, your domain scale is going to be limited on the order of meters. So that's kind of the schematic that you can see over on the right-hand side there, which is showing that tiny little box right at the top, which is on the meter scale. That's what you can get to for these first 2 points, lab experiments or direct numerical simulations. And I should mention, of course, like the scales of kind of an ice shelf can be up to, tens to hundreds of kilometers in width. And so, of course, these meter scale domains are really, really tiny when you think about it in that context. All right, and I will also talk about large eddy simulations as well. So I first just wanted to show some pretty pictures of lab experiments that have been done. So these have kind of been ongoing since the 80s by various different groups. And they've been covering a lot of different processes, ocean processes that we see beneath ice shelves, double diffusive layering, meltwater plume, and these interesting ice scalloping effects. Just because of the limit in time of this talk, I don't have enough time to really go deep on all these physical processes, so I've chosen instead just to take a broad view and show you that there are different processes that we can do in the lab. Here at the University of Melbourne, over in MECEng, Associate Professor Jimmy Phillip has a really nice ice ocean lab experiment going on. And so this is just one example of what a lab experiment might look like. All of this is within like a cold room that you can set to 4 degrees or even just a little bit colder as well. Okay, so lab experiments, again, the domain size of your lab experiment, right, is going to be dependent on the size of your lab, basically, and how much ice you can grow. So you're generally constricted to maybe kind of a meter scale lab experiment. The equivalent in terms of numerical simulations would be a direct numerical simulation. Basically here, you'll be running something on the meter scale, and you're trying to resolve all your scales of turbulence down to the small sub-millimeter scales of the Kolmogorov or the Batchelor scale. So you have to have really high resolution simulations going on here. Some of these figures are a little bit overexposed on this picture, but the top left one does have some nice plumes in it. All right, so over on the left-hand side, I've kind of broken these direct numerical simulations into 2 different ways that you can consider your ice shelf. So on the left-hand side, you have a static ice. So if you can imagine in that top left figure, we have ocean dynamics, plumes going on, and your ice is basically like a horizontal piece of ice that's a boundary condition on your ocean flow. So that's how we're modeling it in the static ice case. On the right-hand side, if you really want to, you can actually do dynamic ice melting. So that grey bit there in the movie, that's our ice, and that's dynamically melting back. On the right-hand side, these numerical simulations, they are more expensive. We just have to go to higher resolution, and so often we are limited in computational expense, but we can get some really interesting results in terms of what the ice topography does under different circumstances. Okay, and I did want to include some equations in this talk. I'm not going to go through all the terms, and I know, I don't expect everyone to really understand each of the terms, but a lot of us, of course, in the climate community, oceans or atmospheres, we're solving versions of these fundamental equations, right, with different assumptions, different parameterizations in them. So I just wanted to make the connection that in the simulations that I'm running, we're running direct numerical simulations here, so we're resolving all of our terms, say, in our momentum equation, and we're basically resolving all of our, heat and salt diffusivity, all of that type of thing. So in DNS, solving these 5 equations, conservation of momentum, mass, heat, and salt. And that bottom one there is the equation of state, which is going to be relating our temperature and salinity of our ocean to the density of our water parcels. And the density is the term, of course, that appears in our momentum equation at the top. And you can choose different equations of state, depending on how complex you want to go. I've just chosen a linear one to put up here. That's probably the simplest. You can do a full seawater equation and get lots of nonlinear interactions, which is really interesting as well. You just add more and more terms to your equation. Depends on what question you're trying to answer with your simulations. And so this slide here is for this static ice boundary condition, that kind of flat ice that's not actively melting back. So if you look at this slide, I'm going to move to the next slide, which is the dynamic ice case. So basically, the way that we model this actively melting ice is to just include an extra term in our momentum, heat, and salt equations. I have simplified things here a little bit. The equations do end up looking a bit more complicated, but the fundamental idea here is that we include a phase field, which we just set to 1 in the ice, 0 in the ocean, and it can actively kind of melt back depending on the temperature and salinity. And so that's what you could see a couple of slides ago in that nice movie. All right, so we've covered DNS pretty well. Just to get back on track here, so I've covered both lab experiments and direct numerical simulations. Again, your domain is on the order of a meter scale domain. But of course, a lot of processes, we'd love to go to a larger domain, maybe do faster currents, or even something like an ocean eddy, something like that. And to do that, we'll move into large eddy simulations. And so the idea with these are you are resolving most of the scales of turbulence in your system, and you're just parameterizing the smallest 3D turbulence, which would be your subgrid scales. Cool, and so I'll go into the next slide here. So I've broken these large eddy simulations into 2 different ways that you can treat the ice application here. So on the left-hand side, I should have mentioned this probably earlier, but if you think about, if you have a horizontal piece of ice and you have your ocean beneath it, right up next to the base of the ice, you get really fine scale diffusive layers forming. And so I'm talking for a salinity layer, we're talking about like a millimeter scale layer right up next to the ice. And so one option when you're running a large eddy simulation is to try and pack enough grid cells right up next to the ice such that you resolve this really fine scale, millimeter scale salinity layer, and you get your melting really correct. So that's what we do in the left-hand side here. And then further away from the ice, we stretch the grid and our large eddy parameterization can kick in, where it's kind of a little bit less important to get everything completely correct. And so I've done some work in this space looking at stratification and current speed, and Maddie Rosevere has done some really nice simulations on double diffusive convection using this method too. On the right-hand side is if you want to go to an even larger domain, so now we're talking about like 3 kilometers, 5 kilometers, you have to start bringing in a parameterization for your ice shelf melting. You can't resolve this millimeter scale salinity boundary layer if you want to go to a kilometer scale domain. So instead, we bring in what we would call a near wall model. If you're in one of the sessions yesterday, there were a couple of talks on large eddy simulations used for the atmospheric boundary layer by Maddie Rosevere and Chris Chapman. And this is probably the equivalent case for the ocean. So they both mentioned Monon-Obukhov similarity that goes into their equivalent to their near wall model. That's what we're trying to do on the ocean side as well. So of course, there are connections to people working in this atmospheric space too. All right, so if you make some assumptions, you put in a parameterization for your ice shelf melting, your first grid point you can suddenly put at 0.5 meter away from the ice, and then you can get to a bigger domain, and you can look at faster current speeds. And this bottom right figure here, it's just a kind of a snapshot picture of some simulations that I did in collaboration with the British Antarctic Survey, where they had some in-place turbulence measurements beneath the Larsen C ice shelf, and we came in and did an LES model, like a side-by-side model with that, and we managed to have some really nice comparisons with the turbulence measurements and kind of help to interpret their observations a little bit further. All right, so large eddy simulations, just two more slides on equations. So basically all I've done here is I've taken those 5 equations that we saw earlier, and then I wanted to highlight that with large eddy simulations, we're just adding in a subgrid scale term here, and there's a lot of different choices you can make in large eddy simulations about what your parametrization looks like, depending on what problem that you want to look at. So this would be for a resolved layer system. Again, that's if you are resolving your millimeter scale layers. The next slide is just for a near wall model where you just have a parametrization for your ice melting. Okay, so this is kind of a summary then of this part 1. Again, I have just chosen to give a bit of a whistle-stop tour of these different types of simulations because I really just want to show you guys that we can take this approach and really tailor it to the problem at hand. So if you've got, a particular process that you want to look at, it could be in the ice shelf ocean interactions, it could be over in the open ocean. Potentially there's scope to run a large eddy simulation or even a DNS, depending on what questions you're trying to answer in your system. And I think a lot more work could be done, by me included, to run these simulations kind of more side by side with observations, because that was really quite beneficial when I did that work with the British Antarctic Survey, and I think there's more scope to do that as well. All right, so you can take your approach, you can tailor it to different problems. And I didn't really talk about this before, so I'll talk about it now. So now I want to relate the type of modeling here back to these large scale, these big challenges that we have in the ice shelf system. So I outlined challenges to do with only being able to take sparse observations of ice shelf melting. And so I kind of already have outlined the fact that we can run these simulations next to those observations and help interpret the obs. The type of simulations, the fine-scale modelling approach that I'm talking about here, can also help us to understand the physics of what's going on and kind of split out different processes. And then also, this is something that I want to do a little bit more now, is to take different processes and see how they interact with each other and how they both then influence the melt rate. So something like a meltwater plume plus tides, or a meltwater plume plus diffusive convection in there. And this will all help us understand the physics better, and both of these can lead into either testing existing parameterizations, like using our models, or even suggesting updates to these parameterizations, which is something that Maddie Rosevear has done recently, and Claire Young has been testing some of these parameterizations in large-scale ocean models, which is really nice work. All right, so that kind of finishes up that first part of the talk. I am going to switch gears a little bit and talk now about my second kind of main topic of research, which is ocean convection and circulation. And to do this, I'm going to bring in this idea of dynamical similarity. Okay, so before I do that, I just wanted to outline the challenges to do with existing challenges that I see that are out there to do with ocean convection and circulation. These kind of mirror, in some respects, the ones that I outlined for the ice shelf melting. But of course, it's also for the ocean, it's difficult to take measurements of the overturning circulation. Like how, if you're running an ocean model, you know what the velocity is at all your grid points. So you can take a cut through and make like a calculation of the overturning. If you're trying to take an observation in the ocean, how do you do that? You can't measure the velocity everywhere. So some people have been working on using like moorings at depth, such as the rapid array group, to make good estimates of the ocean overturning. But it is difficult and expensive to do this because you do need them extended out over a long period of time to start seeing if the overturning circulation is changing. So there's still these difficulties involved with taking measurements. And then there's other similar difficulties with deep convection taking measurements. So I should say here, so this schematic here on the screen is just a kind of a broad schematic of what the North Atlantic overturning circulation looks like. So you've got large scale gyres, and you also have like a vertical overturning circulation. Right in the north, in kind of the Labrador Sea areas, and in some other areas too, you can get deep convection patches. So this is due to cooling of the ocean waters to the atmosphere. You can get deep convection, and this can help to feed into the lower limb of your meridional overturning circulation. And so that's why I'm both interested in ocean convection and circulation kind of together, because they are linked. There's also, so the second point there is saying, look, there's lots of complex physics involved. Again, a lot of different scales, small scale mixing right up to the basin scale overturning. And of course, we can't resolve all of these in one large scale ocean model. It's just not possible. You have to parameterize the smaller scales. And it is, I still argue that it is tricky to have good parameterizations of convection and mixing. There are quite a few different options out there. They all have kind of their pros and cons. Nothing is perfect in this space, and I think there is space to try and keep improving these. And so our approach is going to be a little bit different. I'll get to this on the next screen actually, but it's going to be taking one of our direct numerical simulation models. So this will be a domain on the order of meters. So I sometimes call this like a lab scale model. And we're going to run kind of a very idealized case of an ocean circulation, and then we try and like scale up these results to the real ocean. So I'll explain that in a little bit, but we're going to be doing this using the dynamical similarity ideas. Okay, so I sort of have described this, but just to give you a bit more of an overview, so in terms of length and timescales that we have to do with our ocean dynamics and circulation, large scale we have our overturning and gyre, and right down to the smaller scale we have turbulence and mixing. So yeah, it's impossible to resolve all of these together. So what we plan to do is to actually take this huge range of length scales and make an assumption, and it is a big assumption, I will admit that, but we make an assumption that we can scale this down to a lab scale model. And so the idea behind this is if you know what the important parameters are in your system that are defining your dynamical system, then you should be able to run, say a lab scale model and scale it up to the ocean. This is the same principle that says, okay, for like a turbulent wind tunnel flow, if you match the Reynolds number to a larger scale flow, the dynamics should be the same. And so we argue that for large scale ocean circulation, one of the really important dimensionless parameters here is the global Rossby number, which is the strength of the buoyancy forcing in the flow compared to the strength of the Coriolis parameter. And I've got it up there, our estimate for North Atlantic circulation. There are other important governing parameters also that I'm just not showing due to time. So, if you have wind stress in the system, that also can drive gyre motion. If you have, there's also dependence on other things like Prandtl number and things like that. So they're all important, but I'm just talking about Rossby number here as probably the most important. Cool, okay, so if we make this assumption that we want to run this lab scale model, the way that we've approached it here is we've just taken a really idealized domain, so like a closed rectangular box, and we're heating over half of the top and cooling over the other half. We have a Coriolis parameter in there, and then you can, if you want to, you can put wind stress in there as well. And this Rossby number here, again, the idea is we've chosen specifically, heated and cooled, chosen that whatever that buoyancy forcing is, and then picked an F parameter, a Coriolis parameter, to match the Rossby number that we see in the real ocean. And hopefully you agree with me, I'm trying to hit this home, that the output that we get is quite a similar circulation that you see in the North Atlantic. So bottom left here is going to be our north, apologies for that, but what you can hopefully see is over on the western boundary, you can see a western boundary current forming. It splits off as kind of like a Gulf Stream would, forming into a North Atlantic current, and then recirculates as a large-scale subpolar gyre. And then in this region, you're getting a lot of convection, deep convection going on as well, so that links to the large-scale overturning. And so it kind of, you can see also we're getting like eddies in there as well. So it does still kind of surprise me at how many similarities there are between this very idealized case and the true ocean system, just in terms of, this is all very qualitative of course, but just in terms of those dynamics there. So I'll go to the next slide, which is my last results slide, which is trying to do a little bit more to do a direct comparison with our lab scale experiments. Again, they're numerical simulations, but they're on the meter scale, and the real ocean system. So to make a side-by-side comparison, we do have to go through and do some like non-dimensionalized visualization of both our lab experiment and the ocean system. That's why we're doing things like dividing through depth by the ocean depth, that type of thing. And that's why we've got these kind of complicated looking normalizations going on, but it's really so we can make a side-by-side comparison. So those top two figures are from the observations. Basically, the left-hand side is a zonally averaged version of the stratification in the top, I can't remember off the top of my head, top 1,000 meters, I believe it is. It might be 2,000 meters. And then we've normalized that. And then the bottom figure down here is the same equivalent zonally averaged direct numerical simulation result, and we're showing stratification here. And all I really want you to take away is that the stratification, there are differences, but there's also quite a lot of similarities in terms of the stratification structure. On the right-hand side, we've got temperature salinity plots, and you can see the overall shape of these are very similar, between the two. Keep in mind just how idealized our numerical simulations are when you look at these as well. So there's a lot of differences you can pick out, and that's, I agree with that, but there's also some similarities in there which are a little bit mind-boggling in some ways. All right, so just a bit of a summary on this second topic of ocean circulation and convection. So I've talked a little bit about this dynamical similarity idea. I see this as a complementary approach to large-scale ocean models because we can do a little bit more to test turbulence and mixing. And this last point here about the examining changes in the climate system, that's kind of the research that we're doing now, because we've realized that we can look at past or future climate states using this system, like changing our forcings, and that's quite interesting to us as well. And so this bottom bit here is just me connecting this back to challenges in the system. Again, we can help to interpret observations, maybe a little bit more qualitatively than the side-by-side ice shelf approach. We can gain understanding of the physics. So this, particularly with the Jaya work by Andy Hogg and Bishar Gayan, was a really nice GRL paper a few years back. And then in terms of parameterizations, we can actually test parameterizations of convection using these type of models. And so I'll just go to the last slide, which is a summary of the overall talk. So I've talked through ice shelf melting, ocean convection. I hope I've made the point that we can take these models and we can apply them to a range of different ocean processes and really tailor them to those. And they can help us with our ongoing challenges in terms of measurements, physics, and parameterization. And I've already previously made this last point that the large eddy simulations that I showed here are sort of similar ideas to what was presented yesterday in terms of some of the atmospheric results as well. All right, I'll leave it there. Thanks, everybody.
Thank you very much, Kat. So I'll open the floor to questions. Who's going to start us off? Okay, well, I'll ask a question. Can you talk a little bit more about, on that last slide, about applying this to future climate situations?
Yes. Yeah, so this is a good question. So unfortunately, I don't have an extra slide on this, but at the moment, the results that I was showing was for our current climate state, so in terms of, say, the temperature and salinity forcing. But in future climate states, potentially we're seeing an amplifying water cycle, potentially like more freshening. And so we can put that in our model and see basically what that does to the system. This question, does it shut down convection? We can look at that in our model as well. And I actually agree with the plenary speaker yesterday, Gautam, that when we do these, we also don't see a full shutdown of the AMOC. We see a weakening, but it's not a full shutdown. So we can do those type of modelling as well.
Yeah. That's much HHHR, very high resolution.
I know. How many ultras can we put in front of this?
Anyone else have questions? There's one down at the end here.
Thanks. That was amazing animations. That's really cool work. So there was one, an animation, I think it was DNS, the one where you had like vertical ice and it formed those amazing double diffusive layers.
Yeah.
And I kind of would say, if you start with an ice shelf that was completely vertical, and there's some process that makes it get that cavity, but that's not what's happening in your simulation. So, because it actually looks like it's getting eroded at the top more than anywhere. So what is the process that if you start with a vertical ice shelf, that creates the cavity? Is it just because the water's warmer at the bottom, or?
Yeah, so you're kind of asking, is this one of the processes that you can cause a large-scale cavity? I would probably say, I don't think so. I think it's more, and I didn't have enough time to go into this, but when people take observations of these ice shelves, they see like these scalloping effects on the orders of, say, meters or so. So I tend to think that's more like what we're seeing in this case. We've done it for a vertical ice. If you do it for sloped ice, we haven't actually done this case, but I think you would see some of these effects as well. So that might more kind of apply it to the ice shelf system. Thanks for the question.
Another one here.
I was curious about that plot you showed of sort of the North Atlantic circulation with the little jet coming up western. My question was actually a really simple one. I was curious about what sense the length scale of the plumes and structure on the cold side.
Yeah, so we have a couple of different dynamics going on in here. So the first being the eddies, which is just a typical Rossby length scale. And then the actual convective plumes themselves. So that's related to, it'll be called like the Rayleigh number, basically, the strength of the buoyancy forcing compared to the strength of the smallest effects in your flow, like your viscous and diffusivity. That would change how big your convective plumes are, basically, if that makes sense. Yeah. Not sure if I correctly answered your question, but thank you.
Any more questions? Yes, Terry?
So in the ocean, there are large-scale density compensated modes, spiciness modes that are, sort of advected from the subtropics towards the tropics. They get once they get close to the equator, they become baroclinically unstable, and so I mean there are a lot of these kind of doubly diffusive kinds of ideas that apply to the large scales. So are there analogues of those sort of really coherent, let's say metastable states at the small scales that are impacting the dynamics?
Yeah, this is a great question. It's one that I can't easily answer. I would hazard a guess that yes, we can make some comparison, but again, there are some limitations, of course, with this approach that, yeah, we can't include all the scales, but I would be interested to chat to you to see maybe if there is something that we can directly compare in terms of these metastable states, because hopefully we'd be able to do something in that space. But yeah, thank you.
Okay, thank you very much.
Thanks.
Thank Kat again. Yep.